All right, so hello everyone. Welcome back to the second video for this series. And what we hope to focus on, section two today, is the topic of structural representation and also code and organization. So the first topic is structural representation. So usually this is actually a topic that's not discussed with details in many of the classes right now we have. And one of the reasons is that most likely we work on a specific field. So for instance, civil engineering, um, people will start just drawing these moment resisting frames, this lines without even thinking about what's the abstraction process, because this, for instance, this is going to be representing a building with two bays and three stories. It's been used for hundreds of years, and at this moment people feel that there's no need to really talk about the abstraction process. How do we even end up getting these models? And every node here, if it's a 2D, it should have an X, and then the Y, and then the rotational degrees of freedom, right? That's the abstraction we created, and all the members are beam elements um, or columns, which is also beams essentially. So we just don't talk about it. But here, if we want to talk about active structures, we do have to spend some time talking about this, because many of the objects we're going to be working on, they're new. There's a chance that these objects not yet have a conventional model. So for instance, if you go back, say 15 years or 10 years ago, origami is a brand new topic to study. And how do you model it, right? Then what are the options out there? If you go into these origami modeling field, we actually had a review paper with Mark and also Evgeny on that topic. There's a lot of variabilities and options for you to choose from. They have pros and cons, and so selecting these model representations is actually a big topic for active structures, unlike the more established field. So here in this figure, what I'm showing you is like three primary forms of items that I can think of. Just to give you an idea of what are some of the ways we can represent a system. So the first one here is to use a nodal representation. So we have the node, like this node here. It has the XY translational motion and also the rotational motion, and the two nodes are connected with a beam, and this is used to represent, say, these particular walls, assuming that there's going to be a rebar that's anchored at the base to ensure that this is indeed a rigid connection. So if you just pile a bunch of CMUs or concrete masonry units there, this is not going to be a moment connection, but we do assume that there's going to be some sort of steel there to satisfy these. But this is kind of like a pretty well-established model in civil engineering, for instance. Then in aerospace, for say the wing of let's say an airplane, you do have these expected finite element type of representation for those, and then they represent one of them, nodal coordinate with rotational degrees of freedom. It's a pretty popular one. If you go into any finite element class or a plates and shells, then you probably would be learning something like this. For finite element, if you work on the beam element, that's a typical element that has rotational degrees of freedom. Then the second one are nodal coordinate without rotational degrees of freedom. And for origami, this is being used. For kirigami, it's being used. For many of the other robotic systems, let's say if you want to use cost-rod rods, then you definitely need rotational degrees of freedom. If you use some sort of a pseudo-rigid body model from complaint mechanisms, then you typically don't have rotational degrees of freedom. So that's another one. But at the end of the day, we at the very least typically have the nodal coordinate of some of the critical node that we pick out from the structure. So for instance, these vertices in the crease lines, or these top of this wall and the bottom of these walls, those critical spots we take them out and we create this abstraction to represent a physical system. And do we always need to use nodal coordinates? Absolutely not. So for instance, in origami or in kirigami, you can we're basically dealing with paper folding, right? So we can actually just use the fold angle without any nodal coordinate information. So for instance, here, if I have four creases, four fold, then each of the fold angle is represented here as row 1, row 2, row 3, and row 4. And that's how you can represent the kinematics or deformation of a system like these. So if you're curious about how that model looks like, you can go out and check out the Tomohiro Tachi's really very pioneering work on origami simulation using the link here. I put the link here. It's pretty cool. But anyway, in back to these code packages, the type of the representation we are going to be using is the nodal coordinate without the rotational degrees of freedom. So we're going to be primarily using triangle elements, truss or bar elements, and rotational spring elements to represent the correlated bending and twisting motion with the rotational spring. So we'll talk about those elements and how they are formulated later. So in 2D, if your node has rotational degrees of freedom, it would be x, y, and theta the rotation. In 3D, this would be x, y, x, y, z for translation, theta x, theta y, and theta z for the rotational degrees of freedom. And that's drawn here. This is a 2D case. If you are working without the rotational degrees of freedom, in 2D, it's basically x, y. And then in 3D, it's draw with this figure here is X, Y, Z. So no rotation about those axes. So that's what we're going to be dealing with. And this particular one is what we're going to be dealing with in this code package and also in this living textbook. And you would realize that actually even without rotational degrees of freedom, we are able to simulate rather complicated structures and capture their behaviors quite accurately. All right, so the next thing I would like to talk about is object-oriented programming. And this is a concept, it's a programming concept that's absolutely critical in order to understand any sort of simulation code that you might be using. For instance, if you are really learning these right now, there's a chance that you might be working, let's say, for Abacus to develop some new models, or for COMSOL, or for another new company who's like has some like fantastic new algorithms to create new simulation capabilities for the industry and also for the academic, right? And in order to do that, I don't know about the future of programming with the current AI booming, but then most likely if we continue what we've been doing at this point of the time of human technologies, object-oriented programming is something you would be using to organize your code. And the core behind object-oriented programming is class and object. So let me actually use this Plant versus Zombie game to just briefly introduce what that is. So for instance, you have a pea shooter, right? It basically shoots a pea to kill the zombie, basically. So what a class equivalent would be that little card that you bring with you. It's an abstract virtual item that's not created with physical resources. Say it's a concept, it's a conceptual object. In order for you to be able to use this pea shooter to shoot the peas and to kill the zombie walking towards your backyard, what you need to do is to create an object from a class. And you can create multiple objects from a class, for instance, and then they have similar properties, right? But then and in the code languages, this could be done like this. So PS1 equals P shooter class. That's the MATLAB language that you could use. In Python, you have very similar things. In C or C++, you also have similar things that you can do. And you can create a second one from the same class, the second object. And then the object has these objects, they typically have two type of they have you can define their variables and they have certain functions. So that's the two characteristics that we usually give these objects and class. So for instance, these objects, they may have a location information that's the variable information within that object. So for instance, the PS1 might be in this first row, first column location, whereas the PS2 location is second row, first column, right? That's a way of understanding it. And then the functions would be like asking the object to do certain things. So for instance, you can ask the PS1 to shoot a P to kill the incoming zombie in this game, and that would be something that so this is one of the way that you could imagine to understand what's going on when we say object-oriented programming. So why are we concerned about these? So the primary reason why we need to use it is because it gives us a better way to organize the code, so we can avoid copy pasting code. If you don't do that, let's say if you create functions to represent PS1 and PS2, because there's a lot of properties that's shared, then perhaps you need to, copy paste a lot of the code. And when you want to change them, you have to change them one after another, and that's not ideal. And the other thing that this allows us to do is for a medium size or even like a small size simulation package, there's going to be hundreds of functions. There's going to be many, many different elements and many, many different calculations and algorithms that you can use to solve for the behaviors. So, using these objects just gives you a more readable way to organize these functions and algorithms and allows others to read and also change our code more easily without actually going down deep into the source code. And I would like to demonstrate that later as we get into one of the examples here. So those are the high level um, um, benefits that we get from using it. So without further delay, let's get started with this first example, which is to create this active truss system. It's a 2D truss. The left side of the truss and the right side is probably made up with some active materials that can extend or contract, depending on what kind of stimulus you apply to them. So we're gonna use this example to try to understand how we use these object-oriented programming to actually organize the code package, and most importantly, allows people to easily change and reuse the code even without knowing deep down like what each line of the code is actually doing in the source code package. So here in this simulation code package, the general formulation is that a physical active structures will be represented using a assembly class. So this is going to be assembly class. So if we go to the Living Textbook, section 2, this assembly class is called assembly truss here. That's something, and there's going to be one file that defines the assembly class. So this is class definition. It has 3 properties and 2 methods, or these are functions. These are variables, properties, and methods. That's the 2 name for a class in MATLAB. Okay, let's put it here. So that's the assembly. And under this assembly for the property or the variables, there are 3 of them. They are all objects or classes. So the first one is a node. That's basically the node class. And the second one is a bar. It's a standard truss class or bar class. And the third one is active bar, which is these red members. So the circles are nodes, these black lines are bars, and then these red lines are active bars. So ACT bars, basically. And we need to, from the source code, so let's go back here section to the root SimFest folder. There's this two folder here. That's where all the source code it's stored, and they're all packaged well into this using the object-oriented programming and the class. So here, for instance, that's all the elements. So we have the node, that's the elements node, and we have CD elements that's developed using central difference method, which is something we will learn later. I would save the theory later, but this is just some of the class we could directly use and call and create an object from. And the vect are vectorized elements, so they're faster in computation, not necessarily easy to read and understand. And I believe in these living textbooks, we won't be able to get into the details of them. But if you read papers, most likely when they do analytical derivation, they will be using, they would be more like the vectorized element formulation. But anyway, so let's see what's happening here, right? We first create a assembly called assembly class, and this is and then we create a node from elements node and the bar and the act bar, and then we assign the assembly to assign this node to become the assembly node, and then the bars to become a part of the assembly. So basically, we assign these objects we just created to the assembly so that the MATLAB knows where the code we are actually looking for. So in order to run this pack, what you want to do, let's try to run it right now and see. Let's put a pause mark here. And in order to run this code, you need to tell MATLAB where to find these classes. So for instance, these elements, they are in source code element. So what we want to do is right click that folder, add to path, select the folders. So that command will tell MATLAB to look for these nodes, elements, vectorized elements, and central difference elements in this folder. And following the same philosophy, we will want to add this thing into the folder, so the section 2, because my assembly class is defined in this folder, or I can just simply run it here. So that's how I can run it. And as you can see in the workspace, I've created an assembly class. I've created a active bar, a standard bar, and then a node. So that's how we define the things. So let me show you what will happen if I don't add these things into the path. And let's say if I'm running it here, MATLAB, what will happen is MATLAB will be unable to locate these assembly truss. You see, unrecognized functional variable assembly truss is unable to find that class that's stored here. But if I run, so MATLAB is able to look for functions and classes in the current folder. So if I run it here, I can run it. But if I run it outside, it's not able to run it because the current folder is always in the path. But if this is not added to the path, I'm not going to be able to run it. And if I want to run it here with the current folder being here, what I can do is right click these and then select the folders. And if I run, you would see that, okay, it's able to find the assembly truss. So that's just something to keep in mind. The software usually requires you some sort of way of using it properly so that we know where each of these each of these classes and the functions are located at. All right, that's one of the things. So let's keep going. And oh, before that, actually, I need to add the solver also because later we will need to solve for the structure response. And then after we have the class, we just define the the coordinates of the node. So for instance, so this is basically each line of it is a node, and 0, 0, 0, for instance, would be this node here. Then L0, 0, 0 would be this node, and so on and so forth. It just keeps going up. And then, yeah, so that's just to define the node. And as you can see, within this node element or the node class, there is coordinate mat, so the coordinate matrix that stores the nodal coordinate of all of these, all the nodes. So this is actually a pretty easy to read format, and the naming also makes it easy for people to understand what's going on. And with that defined, we can also plot these. So again, the plot is defined as a class, and it's here the plot truss. So there's a couple of functions you can use, which would plot certain component. So that's the code to operate a plot. We will try not to get too deep into the plot. I'm gonna save that discussion later, but let me show you if I keep running to here what will happen. So that's a live script, so it will show the result here. If you want the result to be shown on the right, you can click here, it's gonna show on the right. But let's show it in line. So we have node 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So those are the 9 nodes that we need to represent this structure, right? So far so good. Looks pretty nice. And after that, we will need to define the traditional bars or the common bars that connect this node, and that's called the node ijmat. So that's basically defining, for instance, the first bar, it will be connecting node 1 and node 2. Second bar is 2 to 5. The third bar is 1, 5. So this one here is kind of very straightforward, right? So that's the nice thing about using object-oriented programming to package the entire code, because it's really straightforward to understand. So for instance, the next thing we want to do is to define those active trusses, so the red trusses, these red trusses here. And the first one would be 1, 3, right? 1, 3, this one. And looking at the nodal, the assigned nodal number, you know, it's going to be 1, 3, 3, 6, 2, 4, and 4, 7. And that's exactly the case. So 1, 3, 2, 4, 3, 6, 4, 7. Those are the 4 nodes. And after that, we just assign the properties of these bars. So that's the mechanical properties. So there's the A vector, so the cross-section area of the bar. The E vector is the Young's modulus of the bar. So those two will give us a way of defining the stiffness of that particular bar system. And after that, after defining these for both the standard bar and also the active bars, we just initialize the assembly and then plots the shape of the bar. Okay, so let's see what we have here. All right, so that's the structure. So the active bars are plotted using the blue color, whereas the standard bars are the dark color. So it looks all good, and it seems that these syntax or these code that we've been working are really just like, you know, human languages, right? So you, what you've been doing, let's say here, plot shape of bar with number. Basically, that's what's there. That's how using object-oriented programming can make your code so much more readable, right? And what you've been doing is I first created this plot from these plot truss function, plot truss class, excuse me. I assign my assembly to that plot, and then I just ask the plot to do the plot shape bar number for me, and then I can get the bars, and then with the nodal with the bar number, so that I know which one bar is the number of each bars, and when I locate the, for instance, the connectivities, I will be able to know. So for instance, this one, 7, 8 bars would be here, and that is exactly the number 10th bar because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, they should match. So that's the nice thing about these. All right. So with that, I would like to just set up a teaser here. So we would not go into the solver too much here. There's going to be two more examples. We would spend more time on the solver, but here I just want to quickly show you what we end up getting. So as you can see, setting up the solver doesn't take that much of an effort when you have object-oriented programming, when all the things are packaged nicely. So I set up these nonlinear solver called the Newton-Raphson Truss Action Solver, and I send my assembly to that solver. I set up the support. So 1 means the node is restricted. 0 means the node are free to move in this is X direction, Y direction, Z direction, right? Quite straightforward. I have 9 nodes because I want to make these a 2D problem. All the Y are restricted. That's all about the support information. And then that's the uh, target length of this active bar 1, 3 to be the original length minus the delta L, and then that's the 2, 4. So 2, 4 is this 2 to be plus the delta L. So if my delta L is positive, this thing should bend towards left, and let's see what will happen, right? Let's keep running our code and see what will happen. So in MATLAB, if you click this hide node, you can hide your node, and then you can have your slider to be more closely put together with with your code. All right. So for instance, that's what will happen. It will try to add the delta L to whatever that's already there. So if I click 0, if I get plus 1, 4, it's like going to plus 1, 4. If I get plus 1, 3, it's more plus like more towards left by 1, 3. So that's what's going on here. So you can just play with these, and that's these active structures to start turning, curling left and right, and that's something quite interesting. But anyway, all right. So that's most of the things I want to show you in these particular sections. In the next videos, what I hope to do is still in the section 2, is to show you that why we create these object-oriented programming. We use that by demonstrating this 2.5 example, where what we will do is just copy paste the code here and basically recreate an example like the one shown in this figure. So less node with one node with these triangle being taller and 2 active trusses here. All right, so with that, I would like to thank you very much for your attention and have a great rest of your day.